Welcome to this lecture number 33 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic that we are currently discussing in the last two lectures is high Reynolds number flows. When typically fluid flows happen at very high Reynolds numbers of the order of few thousands in many engineering applications. Therefore, it is very useful to understand the basics of the fundamentals of fluid flow at high Reynolds numbers. At high Reynolds numbers, the inertial forces are dominant compared to viscous forces in the flow. Therefore, as a first approximation, we can hope to neglect the viscous forces or viscous effects altogether, thereby ending up with the Euler equation, which is simply the Navier-Stokes equation without the viscous terms. This is the inertial part of the Euler equation and the pressure forces plus the gravity forces. Now, upon using a vector identity and by assuming that either, suppose if omega is del cross V is the vorticity of the flow, then either by assuming that flow is along a streamline or another independent assumption by assuming that vorticity is 0, that is the flow is irrotational, we were able to show that the Euler equation simplifies to the Bernoulli equation for a steady incompressible and inviscid flow, that is flow without viscous effects. So, you have P by rho plus half V squared plus G times Z is a constant along a streamline. This is if you use assumption 1, or it is a constant anywhere in the flow if you use assumption 2, that is if you assume that the flow is irrotational. Anywhere in the flow if omega is 0. So, these are two independent assumptions, as I have told you in the last lecture. This is a more stronger assumption, because we are assuming that the flow is irrotational, but it leads to simplification that this is a constant anywhere in the flow. Another, so we also pointed out in the last lecture that irrotationality, although being a kinematic assumption, is more likely to be seen at higher Reynolds numbers when you are far away from solid surfaces. So, we can assume the flow to be reasonably rotational when the fluid flow is happening at high Reynolds number, but close to the solid surfaces rotational effects become important. So, we can imagine the solid surfaces to be sources of vorticity, and the vorticity will be confined close to the solid surfaces, but far away from solid surfaces at high Reynolds numbers the flow is largely rotational. So, when you assume the flow is irrotational, implies irrotational implies del cross V is 0, or whenever you write a curl of a velocity vector is 0, then we can write V as a gradient of a scalar potential. This scalar potential is called the velocity potential. So, inviscid and irrotational flows are also called as, so inviscid plus irrotational flows are also called as potential flows, are also known as potential flows, because the velocity is written as a gradient of a potential. What is the simplification? The velocity is a 3-dimensional quantity in general. It has 3 components, each being a function of all the 3 coordinate directions, but if you use velocity as gradient of potential for irrotational flows, then you need to solve only one unknown function instead of 3 unknown functions. So, only one function to be solved. So, it leads to a lot of simplification. Another simplification that comes is that when you couple this with the fact that the mass conservation equation for incompressible flows becomes del dot V is 0, this means that del dot del phi is 0 or del squared phi is 0. So, this is a Laplace equation. Okay. So, this is a well known Laplace equation, but importantly it is a linear equation. So, the potential satisfies the Laplace equation for potential flows. We also pointed out that the only boundary condition that can be applied is the normal velocity condition, because we have foregone V dot n is 0 on solid surfaces, because we have already dropped the highest order derivative in the Navier-Stokes equation, namely the viscous terms. So, we cannot satisfy all the boundary conditions that are present in the problem, that will lead to an over specification of the Euler equation problem. So, we have to necessarily sacrifice or forego one of the boundary conditions. So, we actually omit the tangential velocity condition in the inviscid flow regime. Now, whether this is really a good assumption or not has to be seen, but already this because the tangential velocity condition is satisfied no matter how high the Reynolds number is. So, clearly the no slip condition is being violated by not satisfying the no slip condition. We are neglecting some physics. How important that is, we will see a little later, and that will be done in the context of what is called the boundary layer theory. But right now let us stick to potential flows, and in the last lecture we mentioned that it is much easier to solve the potential flow, because you have to simply solve del squared phi is 0 subject to V dot n is 0 on the solid boundaries. Now, that is merely del squared phi is equal to 0 is merely a statement of the fact that the flow is irrotational and incompressible. So, the momentum equation, the Euler equation, which has been simplified to the Bernoulli equation for a potential flow, merely serves to determine the pressure. So, the velocity is determined first by solving the Laplace equation subject to the normal velocity boundary condition, and the Bernoulli equation is then used to solve for the pressure in the flow. Okay. There are no viscous stresses. So, once you know the pressure in the flow, then you can integrate it over a solid surface to find what is the net force on a body, for example, okay, which we will indicate a little later. Now, the context in which we started out discussing potential flows is that we provided examples of some simple potential flows. So, we started discussing some simple potential flows. Before that, we also discussed that just as this potential satisfies del squared phi equal to 0 for two dimensional flows, that is when the flow is happening only in the xy plane, we also showed that the stream function also satisfies the Laplace equation, and lines of constant stream functions psi are perpendicular to lines of constant phi, that is the streamlines and equipotentials are orthogonal to each other at each and every point in the flow. So, this is something that we discussed. Then we proceeded to do two examples. We did we found out what is the potential and stream function for what an uniform flow is. An uniform flow is essentially a flow in the xy plane where the flow is constant in the x direction, there is no flow in the y direction. So, u equals u and v equal to 0, and we found that the potential is u times x and the stream function is u times y. We have already solved this. So, the potentials or lines, so lines of constant potentials are found by putting x constant values. So, you will find that lines of constant potential are vertical lines along the y direction, while lines of constant stream function are obtained by putting values of y, because psi is simply u y, which are just horizontal lines, which makes sense for a uniform flow. Then we also discussed line source or sink, which is essentially you have the xyz plane. Imagine you have a source of fluid of mass and where fluid is coming out radially, okay, at each and every point. Since the source length is very, very large, you can imagine it to be like in the xy plane, it will appear like you have a point source and fluid comes out radially at each and every point. Okay. So, this is the, and if it is a sink if all the vectors are radially inward, it is a source if all the vectors are radially outward. Okay. And for this problem we found that the stream function, the velocity potential is m log r and the stream function is m theta, where m is nothing but q by 2 pi b, where b is the length of the source and q is the volumetric flow rate. This is called the source strength. If m is positive, it is a source flow, if m is negative, it is a sink flow. So, we have discussed this also in the last lecture. We then began to discuss what is called line vortex. Okay, that is the topic that we are going to start now. A line vortex is essentially, if you look at the 2D plane, you have fluid flow completely in circular streamlines. Streamlines are completely circular in the xy plane. Okay. So, you have v theta is some constant by r, okay, and v r is 0. Okay. Now, this is the description of the velocity field. So, from this you can find out, use cylindrical polar coordinates. Okay, to find what is the stream function and what is the velocity potential. Velocity potential, so v theta is k by r, is nothing but 1 over r partial phi partial theta, is nothing but minus partial psi partial r, and v r is 0 is partial phi partial r is 1 over r partial psi partial theta. Okay. So, if you integrate the v r equation, we will find that phi, if you integrate this with respect to r, so phi becomes a constant which could be a function of theta, okay, and psi, if you integrate this with respect to theta, you will find that it is a constant which could be a function only of r. Okay. Okay. Now, if you integrate, so that is upon integrating this equation. If you integrate this equation, okay, if you integrate that equation, we will get phi is k theta plus a constant which could be a function of r, and psi is essentially, so if you do this, psi becomes minus some other constant, minus k log r plus some constant which could be a function of theta. If you compare all this, you finally get this. So, these constants must be identically 0, since phi is already k theta. Okay. So, let me see, sorry. Okay. So, phi is a function only of theta. So, this constant is identically 0, I am sorry. Okay. Likewise, this constant, since I is a function only of r, this constant is 0. So, ultimately we get phi is k theta, psi is minus k ln r. These are the potentials and stream functions for line vortex. So, if you look at the expressions, we can finally draw, okay, what are the potentials and stream functions. Okay. So, stream functions are lines of constant r. So, they are circular, 2 dimensions, and potentials are lines of constant theta. So, they will be radially outgoing lines. Okay. these are potentials, equipotentials, and these are constant psi lines. Okay. So, these are three fundamental solutions of potential flows, simple solutions of potential flows. Now, we are going to discuss a very important concept in potential flows, that is, we are going to discuss what is called superposition. So, the Laplace equation that governs the stream functions and potential are linear equations. So, if phi 1 and phi 2 are solutions, okay, of the Laplace equations, then so is some constant times phi 1 plus some other constant times phi 2. So, if you have two simple solutions of the Laplace equation, you can linearly superpose them, and the superposition is also a solution to the Laplace equation. So, if you have two solutions to the Laplace equation, then the any linear combination of these two solutions is also a solution to Laplace equation. So, by combining all the simple solutions that we have seen, we can generate newer solutions which are also solutions to Laplace equation, but we have to then figure out what physical context are these solutions of. Okay. So, that is a task that we have to complete, but all we will definitely have a solution to the Laplace equation, and then we will find out to which problem it is a solution of. It is in fact like the reverse of what we do normally. We have a problem and we find a solution. Here it is almost the reverse, where we find a solution by linearly combining various simple solutions, and then find out what is the problem for which this is a solution of. I am going to illustrate this with a couple of examples. Okay. So, let me do this for what is called doublet or a dipole. So, essentially you have in the xy plane, okay, you have a source at a distance of strength plus m, at a distance minus a from the origin in the x axis, and a sink of strength minus m. Okay. So, we want to know what is the solution for this problem. This is called a doublet or a dipole, because you have a source and sink that are separated by a distance 2a. Now, by the argument I just told you, psi for doublet is essentially psi source plus psi sink, because if psi source is a solution of Laplace equation, psi sink is a solution of Laplace equation, then a combination of that is also a solution of Laplace equation. Okay. Now, we know that if psi is at the origin, source is at the origin, psi is m theta, theta is tan inverse of y by x in terms of the Cartesian variables y and x. If source, this is source at origin, if source is at any location x is equals x naught, y equals y naught, then we can write psi is m theta is equal to m tan inverse of distance from the source becomes y minus y naught and x minus x naught. Okay. In this problem, x naught is minus a, the source is at a distance minus a, but y naught is 0, it is still at the origin in the y direction along the x axis in the y direction. So, psi source for our problem is essentially m tan inverse of y divided by x plus a, and psi sink is essentially minus m tan inverse of y divided by x minus a. Okay. So, psi doublet, which is essentially a superposition of these two, is m times tan inverse of y divided by x plus a minus tan inverse of y divided by x minus a. Okay. So, by linearly combining the two solutions for psi source and psi sink, we have easily obtained the solution for a doublet. Now, we want to take the limit. So, I will first rewrite this as m times tan inverse of y by x times 1 minus a by x minus tan inverse of y by x times. So, if I multiply this by y by x, I will get. So, let me just do this algebra. So, y by x times 1 minus a by x is y by x, okay, minus. So, instead of doing this, let us just delete this step, it is not required. We can take the limit, we want to look at the limit where the distance between the two source, the source of strength plus m and sink of strength minus m, we want to let the distance go to 0 at the same time, but if the distance goes to 0, the source and sink will cancel each other, but in such a manner that m tends to infinity, the strength tends to infinity, such that the product of the distance and the strength tends to 2 times that tends to lambda. Okay. This is the strength of the doublet. Okay. So, in that limit we can simplify this as a tends to 0 psi doublet, this expression, okay, as a tends to 0, this becomes minus 2 in the limit as a tends to 0 becomes minus 2 y a divided by x squared plus y squared, okay, times m. Okay. So, this becomes psi doublet as a tends to 0, m tends to infinity, 2 a m tends to lambda becomes minus lambda y divided by x squared plus y squared. Okay. Or we can say that we can rewrite this as x squared plus y squared psi plus lambda y is 0, or x squared plus y plus lambda by 2 psi whole squared is lambda by 2 psi whole squared. Okay. So, as a becomes very small and m becomes very large, and such a manner that a times m is a constant, the doublet, okay, essentially becomes like this. Okay. So, the stream functions are circles. Okay. You have to, in order to plot a stream function, you have to put psi equal to constant. In order to plot streamlines, you have to put psi equals constant, and you have to simply draw the curve. You will find that these are essentially circles like this of. So, essentially the source will tend to push the fluid in this direction, the sink will tend to attract the fluid in this direction. So, the direction of flow is like this. So, source is trying to push the fluid like this, the sink is trying to attract the fluid, and the equipotentials will be perpendicular to this. Okay. So, we have to draw circles that are perpendicular to at each and every point, and so on. Okay. So, those are the equipotentials, okay, and the potentials are also easily derived for the doublet. So, by superposing the two solutions and getting the limit as a tends to 0, you will get this is lambda x by x squared plus y squared, okay, and these are also circles, but in such a manner that they are orthogonal to the streamlines. Okay. The equipotential also circles. Okay. Now, so we have these two expressions psi doublet and phi doublet. Psi doublet is minus lambda y divided by x squared plus y squared. Okay. Then from geometry we can write this in cylindrical polar coordinates as, okay. So, this is x by x squared plus y squared is nothing but, so if you look at the polar coordinates, you have r theta. So, this is x is r cos theta. So, lambda r cos theta divided by r squared. So, this becomes lambda cos theta by r, this becomes minus lambda sin theta by r. So, these are the expressions for doublets. the stream functions and velocity potentials for a doublet. So, the doublet is again a solution that is a mathematical abstraction, but it is nonetheless a solution to potential flow, in which case wherein you have a source of fluid and a sink of fluid in such a manner that of identical strengths, but source has positive values and sink has negative values, in such a manner that you bring the source and sink together, but the distance, as the distance goes to 0, the magnitude of the source or sink strength also goes to infinity in such a manner that A times m, that is a product of these two, tends to a constant lambda, okay, twice of that tends 2 times A times m tends to a constant lambda, and in that limit you get what is called a doublet or a dipole. Now, although the dipole by itself is merely a mathematical abstraction, we will soon see that the dipole plays an important role in finding what is the flow pattern for potential flow past a cylinder. Okay. But before that, I want to discuss one important example, that is that of a what is called a Rankine half body. Okay. Suppose you have a source at the origin. So, in cylindrical polars, source at the origin means the stream function is m theta and a uniform flow in the x direction. So, let me draw the coordinate direction. You have x, y, you have a source at the origin plus m, and far away you have uniform flow in the plus x direction of velocity u. So, the uniform flow has potential stream function u y, y is r sin theta. So, I am writing this as r sin theta. So, this is the uniform flow, and I am adding it with source at the origin. Okay. Now, if I were to plot the stream lines by putting in values for psi, we will find that you get far away, you get flow like this. Okay. Now, close to the cylinder, close to the origin, you have the source which will try to push fluid in this direction, but they will be soon convected away by the uniform flow in the plus x direction. So, the streamlines will look like this, but there will be another streamline like this. But there will be one streamline which will be essentially like a closed surface. Okay. Now, this streamline, okay, so this is a streamline that is completely like a surface. Okay. This is called a half body, because it is almost like a sort of an elliptically shaped body, okay, and there is fluid flow past that solid surface. Now, what is important to understand is that whenever you have a streamline and you have flow past a potential flow and there is a streamline, okay, the streamline can be essentially treated as a solid body, because within the potential flow, within the realm of potential flow, we can satisfy only the normal velocity condition, and there is no flow across the streamline. There is no way we can satisfy the tangential velocity condition within potential flow. So, if you have a closed streamline like this, that means that fluid is flowing past such a closed streamline. So, you have flow like this, okay, and you may have flow like this. Okay. So, in fact, fluid is flowing past this shaped body, that is called the half body. So, what I am trying to say is that by just merely superposing two simple flows, a uniform flow and a source at the origin, we are almost getting the potential flow solution to a flow past a solid body. Okay. Along the same lines, we are now going to understand what is potential flow past a cylinder. Okay. It is a very important problem. So, essentially you have a long circular cylinder, okay, and fluid is flowing like this. So, potential flow past. Okay. How are we going to get this solution? So, essentially if this direction is very long, we can just we can essentially simplify the problem to look like on the plane it is like a flow past a circle. Okay. How are you going to simulate this flow using the simple potential flows, using the simple potential flow solutions? Well, you superpose a doublet of strength lambda and uniform flow with velocity u. Okay. So, essentially you superpose these two. We know what is the uniform flow potential, which is u x, and we know what is the doublet potential, or similarly we know what is the uniform flow stream function, we know what is the doublet stream function. We just derived this. I am going to tell you, I am going to show you or demonstrate to you that these correspond to potential flow past a cylinder. How are we going to do that? Well, instead of x, I am going to put r cos theta, polar coordinates. Instead of y, I am going to put r sin theta. So, psi becomes u r times 1 minus lambda by u r squared if I take sin theta. Okay. Now, and phi is u r times 1 plus lambda by u r squared times cos theta. Now, we can ask the question, what are the velocity components? V r is partial phi by partial r is nothing but u minus lambda by r squared times cosine theta, and V theta is 1 over r partial phi partial theta, which is nothing but minus u 1 plus lambda by u r squared sin theta. If you ask the question, when is V r 0? Okay. V r is 0 by looking at this expression when u equals lambda by r squared or theta becomes pi by 2, 3 pi by 2. Okay. So, along those lines V r is 0. Okay. So, either V r can be 0 when either this quantity is 0, when u is lambda by r squared, or when cosine theta is 0. Cosine theta is 0 when theta equals pi by 2 or 3 pi by 2. Okay. So, when you look at this, okay, this simplifies to when r equals the radial coordinate is root of lambda by u. So, when r equals, when the radial distance r equals a constant, okay, that is which is essentially shape of a circle in 2 dimensions, there is no normal velocity. V r is 0 along a circle. That means that there is a closed streamline, okay, in the problem in which V r is 0. That is a definition of a streamline, because you are essentially putting a constant value. So, you can also look at the psi value when lambda when r is equal to square root of lambda by u, you will see that the stream function value is 0. So, that is a line of constant stream function, which is essentially a streamline. It is a circle. So, it is almost like flow past a circle, which is essentially 2D flow past a cylinder. Okay. So, by superposing a uniform flow with a doublet at the origin, we have simulated potential flow past a circle or a cylinder. Okay. Now, far away, as r tends to infinity, okay, if you look at this expression, as r tends to infinity, V r becomes u cosine theta. That is a uniform velocity, radial component of the uniform velocity. But the velocity is V x times I plus V y times j. There are 2 components, okay, or we can write it as V r E r plus V theta E theta. Okay. But E r can be expressed in terms of E x and E y or I and j using geometry. Okay. Cos theta times I plus sin theta times j, and E theta is nothing but minus sin theta times I plus cos theta times j. So, we can write the velocity, we can plug this values of E r in terms of I and j out here, and then write the velocity in Cartesian coordinates, which essentially becomes u. Okay. So, v becomes v r times cos theta I minus plus sin theta j plus v theta times minus sin theta I plus cos theta j. As r goes to infinity, okay, we will find that the velocity vector is essentially, okay, if you simplify this, you will find that this is u cos squared theta I plus u cos theta sin theta j plus u sin squared theta I minus u sin theta cos theta j as r goes to infinity. So, these two terms will cancel to give the velocity to be just u times I. It is the uniform flow. Okay. So, essentially we have solved for what is the velocity field for flow around a cylinder in the potential flow regime by simply superposing the uniform flow far away with a doublet at the origin, okay, and that gave rise to essentially a closed streamline of radius square root of lambda by u, where lambda is the dipole strength and u is the strength of the uniform flow, and this gave rise to flow past a cylinder. Okay. We will now compute what is the pressure force on a cylinder. So, having solved for the velocity field in the potential flow regime for flow past a cylinder, okay, a long cylinder, we are now ready to compute the pressure force. Okay. So, the pressure, if you remember, should be calculated from the Bernoulli equation. So, v squared by 2 plus p by rho plus g z is a constant in a potential flow. That is the statement of Bernoulli equation for inviscid incompressible irrotational flows. Okay. And if you assume that the gravitational effects are unimportant, because everything is at I mean the distances are very, very small. So, there is no effect of gravity. So, essentially we will have p by rho plus v squared by 2 is constant. Okay. So, as r goes to infinity, v, the velocity vector is u times I, we just derived that, and the pressure is some constant pressure p naught. Okay. So, the constant that we want far away is p 0 plus u squared by 2. So, this is that constant, because you can fix that constant by looking at what the pressure and velocities are at p by rho plus u squared by 2. Now, we want to calculate what is the force on the surface of the cylinder due to pressure forces at the surface of the cylinder, square root of lambda by u. Okay. At theta equals, suppose you put a coordinate system, okay, this is theta. Okay. Now, at theta equals pi by 2, v theta is minus 2 v naught, at theta is minus pi by 2, that is if you go like this. So, here v theta is minus 2 v naught, okay, and out here v theta is 2 v naught. Okay. Okay. So, at r equals r, v r is 0 by definition, because there is no normal velocity into the surface of the cylinder. That is how we identified that it is, there is no normal velocity at the streamline when r equals r, capital R equals lambda by u. So, the only velocity you have to worry is v theta, which upon putting r is the radius, you get minus u times 1 plus lambda by u capital R squared sin theta. Okay. Now, r squared is nothing but lambda by u by definition, that is how we define the radius of the sphere. Okay. So, v theta evaluated at the radius of the cylinder, I am sorry, is minus 2 u sin theta. Okay. So, this is the point I was trying to make, it is to u, there is no v naught, it is just u Okay. This is the free stream velocity far away. Now, we know that p by rho plus half v squared is constant. So, p at r equals r by rho plus half v squared evaluated at r equals r is p at r tends to infinity by rho plus half v squared r tends to infinity. Now, this is nothing but p naught by rho plus half u squared and p at r equals r, which is what we want, plus half v squared r equals r. Now, this is nothing but half times minus 2 u sin theta. There is no r component, there is only theta component, which we just evaluated at r equals the radius capital R. So, eliminating therefore, the pressure p at r equals r minus p naught is rho u squared by 2 times 1 minus 4 sin squared theta. Okay. Okay. So, this is the pressure. Now, we look at this from the context of the coordinate system. You have x, y, flow is far away in the x direction. Okay. And now, if you look at various points, look at this expression when theta equal to 0, okay, sin theta is 0. Okay. So, let us assume this to be theta. When theta is 0, sin theta is 0. So, the pressure takes the value at, so pressure at r equals r is only a function of theta, pressure at theta equal to 0 at r equals r. So, we are fixing r equals r, okay. Pressure at theta equal to 0 minus p naught, which is the constant pressure, is rho u squared by 2. Okay. Now, pressure at theta is pi by 2. When theta is pi by 2, sin theta is 1. So, this becomes 1 minus 4, which becomes negative, okay, compared to the free stream pressure. Okay. So, this becomes minus p naught is rho u squared by 2 times 1 minus 4, which is minus 3. Okay. Okay. Now, when pressure at theta is, if you go around 3 pi by 2 minus p naught, sin theta is again 0 at a value of sorry, not 3 pi by 2, pressure at a value of pi, sin pi is again 0, we will again get rho u squared by 2, and pressure at the value of 3 pi by 2 minus p naught, we will again get minus 3 rho u squared by 2. Okay. So, the pressure is a maximum at these 2 points, and pressure is a minimum at these 2 points, and the variation of pressure over the surface is symmetric. Okay. There is complete symmetry about this, there is a complete 4F symmetry about the half of the cylinder. There is a complete symmetry of the pressure variation, okay, because the pressure is an even function of theta, because you have 1 minus 4 sin squared theta. Okay. So, it is an even function of theta. So, there is a complete symmetry of pressure. The pressure value here will be the same as the pressure value here, because you have sin squared theta. Okay. So, it will be the same if you are, whether if you are here or here. Okay. So, now once you find what is, so the pressure is completely symmetric in the about this axis, it is called 4F symmetry. Okay. Once you have found what is the pressure, okay, we can find what is the force. The force on the object is only due to the pressure force. The pressure exerted by the fluid on the surface acts inward, because if the outward unit normal is n, inward normal is pressure acts in the direction of minus n. So, ds is nothing but r d theta. This is the force per unit length of the cylinder, okay, because it is a long cylinder. So, this is force per unit length. Now, by symmetry, since the flow is in the x direction, we can imagine that the only force should be in the x direction, because there is nothing in the y direction to suggest that there will be a net force in the y direction. So, by symmetry we can say that the only force that we have to calculate is in the x direction, is minus p. Now, n is nothing but E r dot I, and then ds is r d theta, where r is the radius of the circle, okay, and the pressure is simply minus rho u squared r by 2 times 1 minus 4 sin squared theta times cosine theta d theta. So, the x component of the force is nothing but minus rho u squared, okay, and sorry. So, before I do that, okay, I look at this expression. So, theta is going from 0 to 2 pi. So, this is equal to minus rho u squared r by 2, theta is 0 to 2 pi, okay, 1 minus 4 sin squared theta, okay, d theta of sin theta is cos theta. So, instead of cos theta d theta, I will write d of sin theta, okay. So, it is d of sin theta, okay. So, you have a very simple integral wherein you have an even function of sin theta, okay, an even function of the argument, and theta goes from 0 to 2 pi, okay. So, if cos theta is written as x, okay, dx by d theta is essentially sin theta d theta, okay. So, dx by d theta is sin theta, or d theta is dx by sin theta, okay. So, you can evaluate this integral by using this change of variable, and we can show that f x is identically 0. And similarly, we can also compute, if you do not invoke symmetry, you can also compute the force in the y direction. It becomes rho u squared r by 2 1 minus 4 sin squared theta times sin theta d theta, and that also becomes 0. So, f y this also becomes 0. So, if you have flow past uniform flow past a circular cylinder, okay, of some radius r, okay, what we are finding, okay, you have uniform potential flow, in a potential flow there are no viscous effects, because the viscous effects are set to 0 when we went from the Navier-Stokes to Euler equation, and the only forces are due to fluid pressure. So, the stress tensor has only the pressure contribution, there is no viscous stress contribution. So, the force exerted by the fluid on the cylinder is identically equal to 0. So, this comes as a surprise in the potential flow limit for potential flow. This comes as a surprise because experiments tell us that even at very high Reynolds numbers, whenever you have potential flow past any object like a long cylinder or a sphere, you always find a finite force that is I mean, if you move a sphere or a cylinder at very high Reynolds numbers, then you do find that there is a force experienced by these solid objects. But when you try to treat that within the potential flow approximation you find that there are no forces. So, that this appears like a paradoxical situation, and this is called the Alembert's paradox, that the potential flow solutions give rise to zero force on solid objects such as cylinder, a long cylinder. When you find the pressure profile and integrate the pressure, you find that the pressure is identically, the force due to pressure is identically 0. So, this leads to a contradiction or a paradox, because experimentally these objects do experience a finite drag force, okay, when they move in a fluid. So, there is a force, resistance force exerted by the fluid on the solid objects, but they come out to be 0 identically in the potential flow approximation. So, this forces us to rethink our approximation itself, because as I mentioned in the beginning, when we went from the Navier-Stokes Euler equations, we neglected the viscous terms completely, assuming that they are multiplied by a small number 1 over Reynolds number. That assumption meant that the gradients of velocities are uniformly small everywhere in the flow, and this also led to the sacrifice of the no slip condition, because we were not able to satisfy all the boundary conditions of the problem. So, this already signals where we could have gone wrong, namely that when you neglect the viscous terms, probably the neglect is okay when you are far away from a solid surface, but close to the solid surface we cannot completely neglect the viscous terms, because it is where the velocity will change from whatever it is there a little away from the solid surface to 0, because the no slip condition is always satisfied by a fluid regardless of the Reynolds number. It is a physical condition that is independent of the Reynolds number. No matter how low or how high the viscosity of a fluid is, the no slip condition is always satisfied. Therefore, one has to revisit our assumption of sacrificing the no slip condition in the potential flow approximation. Now, that is what is done in what is called the boundary layer theory, wherein we now are going to say that the potential flow approximation is not a bad approximation when you are far away from the solid surface, but close to the solid surface we have to re-invoke the viscous effects even at high Reynolds numbers. And when you invoke the viscous effects at high Reynolds numbers, okay, by suitably approximating the viscous terms, then we are bringing the viscous terms back into the governing equations, and then we have the ability to satisfy both the normal velocity and tangential velocity conditions, and that region close to the solid surface where viscous effects dominate is called the boundary layer. Now, by including the viscous forces, then we now have hope of obtaining a finite drag, because now the net force on a solid surface is not because of just the pressure forces, but close to a solid surface where the boundary layer is, viscous effects also become important, and therefore, we can now have hope of getting a non-zero force. Now, that is the subject of boundary layer theory, which I will start in the next lecture.